Welcome to Study Loop.
Problem 8.77. We have two cars, a sedan A traveling to the south and an SUV B traveling to the west. Their masses are given here. They run into each other, as cars do, and slide together for some distance along the ground. Now we're told the distance which they slid together before stopping, and we're given the x and y components of that displacement. We're told what the coefficient of kinetic friction is between the combined cars and the ground. And now what we want to do is figure out what were the speeds of the cars before they had the collision. So this is going to have two steps. The first, we're going to be thinking about energy, and in the second, we're going to be thinking about momentum. So a little bit of preliminary here. We want to know what d is, and that's easy. We just use the Pythagorean theorem. So d is equal to 8.39 meters. And we'd also like to know what theta is. Theta is the arctangent of the opposite over the adjacent sides. And this is about 50 degrees. So, little Roman numeral 1 here. We know that in order to be sliding in the first place, the combined car object had to have some kinetic energy, and we'll call ma plus mb big M, and their speed right after they started sliding will be just v. And now in order for this to have stopped, some amount of work had to have been done on it to get rid of the kinetic energy. That work was done by friction. So we know that work is the force times the distance over which the force is exerted. Now, then the force of friction is the coefficient of friction times the normal force, which of this is just the weight. So big M times G, and then the distance we've called D. So the speed they were going immediately after the collision is the square root of 2 times the coefficient of friction times the acceleration of gravity times this distance. They were going 11.1 meters per second together right after they hit. Now, in order to use this for the conservation of momentum, because it is a vector, and we're going to take advantage of the fact that we know the initial velocity of A was entirely in the y direction, and the initial velocity of B was entirely in the x direction, in order to make our lives easier with doing the conservation of momentum calculations. Or in fact, I mean, we'd need more information that we wouldn't have if we didn't know what the directions of these were already. So let's turn our v into a vector before turning our attention to momentum, or we could think of this as the first part of turning our attention towards momentum. So this is going to be the magnitude of this times the cosine of the angle, the unit vector in the x direction, and the sine of the angle, the unit vector in the y direction. And just so we don't have a bunch of negative signs that we don't really need, we'll let left be the positive x direction and down be the positive y direction. So you work this out and you find that the velocity vector immediately after the collision was 7.14 meters per second in x and 8.5 meters per second in y. Okay. So now the momentum of the combined cars together is the sum of their masses times the velocity we just found. And then the momentum from A will be its mass times its speed times the unit vector in the direction it was going. And similarly for B. And now just breaking this apart, we'll find that VA is equal to big M over MA times the y component of our velocity here. And this works out to be 21 meters per second. Now the speed of the SUV has the same sort of form to the equation because there's nothing special about one or the other in terms of the physics involved. Maybe one of them had a nicer color than the other. There's no way for us to know. This was going 12 meters per second. So perhaps the SUV was slowing down and trying not to run a red light and didn't do it in time and got hit by the sedan, or who knows what, we're not told. But in any event, these are how fast they were going before the collision, and we've worked backwards from what the results were to what the initial conditions were.